If you consider the nature of Earth's atmosphere, it can be understood as a relatively thin but vital layer of various gases that envelopes the entire planet, forming a protective shell around it. This layer is composed primarily of nitrogen, which constitutes the majority of the atmosphere, but it also contains a significant amount of oxygen, which is essential for the respiration of most living organisms, including humans. Additionally, the atmosphere includes greenhouse gases that play a critical role in maintaining the planet's warmth by trapping heat energy, as well as the ozone layer, which shields life on Earth by filtering out the sun's most harmful ultraviolet radiation. One of the key characteristics of the atmosphere is that the density of the gas particles is greatest near the Earth's surface. This means that the number of particles in a given volume of air is much higher when you are close to the ground, and this density decreases steadily the farther you move away from the surface. As a direct result of this decreasing density, the pressure also becomes lower the higher you go in altitude. In this video, we are exploring the concept of atmospheric pressure and examining why it behaves the way it does with changes in elevation. One of the major reasons why atmospheric pressure decreases with height is directly linked to the reduction in the number of gas particles as you ascend. To better understand this, imagine plotting a graph that shows how atmospheric pressure varies with height above sea level. When we compare two identical objects, one positioned at sea level and the other placed at an elevation of 1,000 meters above the ground, we find that the object at sea level is surrounded by a far greater concentration of air particles. These particles are in constant motion and collide with the surfaces of objects, exerting force in the process. Since the object at sea level is bombarded by more particles due to the higher density, it experiences more frequent collisions and therefore a stronger net force from the surrounding air. In contrast, the object higher in the atmosphere will encounter far fewer particles and fewer collisions. According to the fundamental equation for pressure, pressure is defined as force divided by area. So, a greater force acting over a given area results in a greater pressure. That means the object at sea level feels significantly more pressure simply because more air particles are hitting it constantly and exerting more force. In simple terms, being closer to the surface of the Earth subjects any object to higher atmospheric pressure due to both increased particle density and more intense molecular collisions. However, that is only part of the story. Another major factor that influences atmospheric pressure is the weight of the air above the object. Air, like any other substance, has mass and is therefore subject to the force of gravity, which gives it weight. An object resting at sea level is essentially located at the base of the entire atmosphere. This means it supports the full weight of all the gas particles above it, stretching all the way up to the edge of space. This considerable weight contributes additional downward force on the object, thereby increasing the pressure it experiences. On the other hand, an object situated at an altitude of 1,000 meters has a much smaller volume of atmosphere above it and therefore a significantly reduced amount of weight pressing down. With fewer gas particles overhead, the gravitational force acting on the column of air above the object is less, resulting in a lower pressure. This gradual reduction in atmospheric pressure with altitude is the very reason why mountain climbers are often seen carrying oxygen tanks when they attempt to reach the summits of high peaks. At high altitudes, the air becomes so thin that the concentration of oxygen in each breath is insufficient to sustain the body's needs. Without the additional oxygen supply, climbers would quickly experience difficulty breathing due to the drastically reduced atmospheric pressure and the corresponding lack of available oxygen molecules. Anyway, that brings us to the end of this explanation. Hopefully everything made sense and helped deepen your understanding of how atmospheric pressure works. Thanks for watching, and we hope to see you again in another lesson soon.